Hello, everyone. My name is Valerio. I'm a PhD student from the university. Can I talk? Okay, I can talk like this. Okay, so this is fine. So my name is Valerio. I'm a PhD student at the University of Cologne. And in these 10 minutes, for which I thank the University of Exeter and the organizers, I will talk about my first PhD project. And the topic is the innermost region of the young stellar object HD 141569. As mentioned yesterday, the innermost region of planetary disks are of prime interest because key processes like gas outflows, gas accretion, and dust sublimation take place, and they affect the evolution and the dynamics of region where terrestrial planets may form or migrate over a few mega years. Even though statistical studies of large WSO samples are of higher relevance, some systems require a more in-depth analysis due to their particular nature and unusual evolutionary state. And HD 141 is one of these objects. Indeed, observation with many instruments at a different wavelength have shown a very complex and wide circumstellar environment made by multiple dust rings, gaps, and spiral arms. Also, a significant amount of gas was detected, CO emission ranging between 10 to a few hundred parsecs, and hydrogen line emission were constrained inside the first 1.2 AU of the system. Very little information are known about the very inner regions. The system was observed with millisecond resolution through the Keck interferometer and with Pioneer, but the instrument were not able to resolve the system. With the fact that dust was not detected inside the first 5 AU, and in combination with the fact that the K-band measurements reflect featureless spectral energy distribution within 5%, spectral energy distribution modeling led to the conclusion that the innermost region of this system is dust depleted. But we know from past studies that many Hebrew stars show a hot dust component. So we observed HD 141 with gravity, and gravity marginally resolved the system with square visibility down to 0.8. The closure phase signals fluctuate around 0, so we can say that the emission is centrosymmetric at our spatial resolution. There is 1.5 milliseconds for the longest baseline. And the visibility square modeling suggests that at around 1 AU, there is a ring made of hot dust, small in width, and that is coplanar with the outer rings. The rings account for 6% of the total K-band flux emission, so it's very faint, and this can be one of the reasons why the Pioneer instrument were not able to resolve and to detect such faint excess. To understand better the nature of the dust particles and to reinforce our findings, we model the spectral energy distribution through radiative transfer modeling. So the first step was to create a model of silicate grains based on the findings of the gravity results. And we played with the parameters of our model, mainly the dust mass, the dust particle size, and the presence or the absence of carbon particles. And we found that these silicate models can reproduce the 6% flux excess in the K-band, but they also have a significant amount of flux emission in the mid-infrared that is not consistent with the spectral energy distribution of the system. So we tried to look for other solutions, and we noted that in the literature, For two objects, for other two young stellar objects, quantum ether particles were invoked to explain the presence of hot dust in their disk cavity. So we tried a quantum ether particles disk model, and we found out that a small amount of such particles can reproduce the faint K-band flux excess without having a significant contribution on the mid-infrared emission. The small width of the ring can raise some question on the origin of such ring. And first of all, other gravity data analysis for other systems led in two cases to small width, to small ring width, but several scenarios have been proposed for the different protoplanetary disk structure. For example, the dust trap to companion presence, self-induced pileup of particles by aerodynamical feedback, and fragmentation of wide rings due to secular gravitational instability. So further analysis and further modeling are required to discriminate between these competing models. So thanks to gravity, we can also gain information on the Berkeley gamma line emitting gas region, mainly with the help of the differential phases. The differential phases are a powerful tool, powerful observables, because they can give us information on the cinematics of the gas in angular scales that can surpass the nominal resolution of the interferometer. So from the differential phase, we derive the pure line photocenter shift, and we can see that they are aligned. They are all aligned with a position angle consistent with the outer rings. We note also that the blue shifted points are located toward the southeast, and the red points are located toward the northwest. And this can be interpreted as a gas disk in Keplerian rotation. To verify this, we created a geometrical model of a Keplerian disk, which the images are shown in the top. And from the images, we calculated the photocenter shift and the differential phases, and we noted that they are consistent with the gravity observation. Lastly, we note that in the photocenter shift, especially in the red part, there is some kind of deviation from Keplerian motion. This can be explained with the presence of a low mass companion, but it can also be due to our limitation from the spectral calibration. We note that the spectrum of the system obtained with different instruments at different epochs is fairly constant, but the spectrum obtained with gravity is not symmetric as the other ones. We see that the red peak is weaker than the blue peak. So to reinforce our findings, I calculated again the photocenter shift from the gravity differential phases, but in combination with the symphony spectrum. And we saw that the first order Keplerian motion still remains, but also the deviation from Keplerian motion in the red part of the disk still remains. So a final analysis is required to better understand what is going on in this innermost region, for example, with observation with the UTs. So summarizing, the innermost, the first 1 AU of HD 141 was partially resolved by gravity, and the detection of a hot dust ring coplanar with the outer rings is now more robust. It accounts for 6% of the total flux in the K band, and it is consistent with the flux excess in the spectral energy distribution that before was thought to be absent. With radiative transfer modeling, we found out that a quantum-weighted particle made ring can explain this such faint excess. And we also found out that silicon model cannot reproduce such small excess without having a significant emission in the mid-infrared. And from the pure line differential phases, we constrain the bracket gamma gas region to be in Keplerian rotation inside with a size of 13 stellar radii. But deviation from Keplerian motion were observed and have to be better assessed. So I thank you for your attention and
okay, thank you very much. We already have a question online from Alexis Matter, who says, very interesting talk, thank you. In your radiative transfer model, would more traditional micron-sized carbon grains or any featureless grains in the mid-infrared at thermal equilibrium work too? Do you really need QHPs?
So we tried to add carbon particles in our radiative transfer modeling. So we tried silicate with different sizes ranging from 2.5 micron to 300 microns, and with and without carbon. And in both cases, the mid-infrared excess would surpass what we observe in the spectral energy distribution of the system.
Great, thank you. Do we have any questions from the room? Please introduce yourself before you say your question. Thank you.
Okay, I'm Lei Chen from Concordia Observatory, Budapest. So I have two questions. One is that you need these very small particles to account for the K-band emission at 0.8 AU, right? But then my question is, could these small particles survive the radiation pressure from the star? That's my first question. And the second is this, you need only 6% of extended emission. So could this just be the scattered light from the out disk? So do you really need in a K-band range?
So for the scattered light, we also tried to model the continuum data with a halo component. So we tried in two cases. So the unresolved star plus a ring and unresolved star plus halo plus ring. And we found out that the halo contribution is very close to 0%. So from our modeling, there's no scattered light contribution. For the question on the star radiative pressure on the particles, so the quantum with the particles behave in a different way that normal dust. So they absorb the ultraviolet emission from the star and they re-emit in the near infrared. So they do not have a thermal equilibrium temperature, but the temperature can range from tens of Kelvin to 2000 Kelvin. So so the question was if they can survive the star pressure, and I don't have an answer for that. So further analysis, I think, would be needed to see if they can.
Thank you.
Great. Do we have any more questions? Cool. Perhaps I can ask a question. So you mentioned that you want to get observations with the UTs. Is this to help find the companion or just to get a better handle on the fluxes? And also, do you have any other observations that you think could assist in further constraint of the system?
Of course, with the UTs, I mean, we would have a better UV plane coverage, and we would have a more data on the squared visibility, so the error bars on the parameters would decrease. But the main point would be to look if the Keplerian, the deviation from Keplerian motion is still present or not. Okay. So the UT is having, would help in the sense.
Okay, great. Thank you. Any further questions? Okay, we're just about on time, so thank you very much. Let's thank Valerio again.